Okay, so we have an expression for sigma x. We have an expression for tau xy, and we know the expression for sigma y. So all of that is good, but that's not what we were looking for. We're looking for displacements. So to derive the expression for beam displacements, we start with we start with this expression here. Epsilon x is partial u partial x, but we have sigmas, we don't have epsilons. So what do we do? Who do we call? We call our main man Hooke, and we change the stresses to strains through Hooke's law. So there's the E being inserted into the stress equation. Epsilon y is not 0. That would be a terrible mistake if you said epsilon y is 0. Sigma y is 0, but epsilon y is not 0. Hit the pause button if you didn't understand what I just said. It's related negatively through Poisson's ratio. That's the Poisson effect. So this is our second equation for epsilon. For the first equation is for epsilon x. The second is for epsilon y. And then the shear strain is partial u partial y plus partial v partial x. We know that through Hooke's law is tau over g. We don't want to introduce g at this point. You remember from your sophomore level class that g can be expressed in terms of e. Over 2 times 1 plus nu. So partial u partial y plus partial v partial x is 2 times 1 plus nu over e times tau xy, which we just found. So here's the expression for tau xy, and I'm going to call that equation C. So now, let's think hard about what's going to happen here. I have epsilon x is partial u partial x, and I'm looking for u, so I have to integrate this. What will I pick up when I integrate A? What will I pick up when I integrate B? Are they constants of integration, or are they functions of integration? Hit the pause button if you don't know the answer. The answer is functions of integration. So I integrate u, and I pick up a function of y because I'm integrating with respect to x here. And then v, I'm integrating with respect to y, so I pick up a function of x. And this is the, interesting and subtle. It's slightly different than what we've done before. So now I'm going to pop it into the strain equation, partial u partial y plus partial v partial x. And here, partial u partial y becomes du dy because u1 is only a function of y. So partial u partial y switches to du dy. We've seen this several times already. Here's the derivative of this term with respect to y. And now we're differentiating equation E with respect to x. Again, this is not a partial anymore. It's a regular derivative because v1 is only a function of x. So a partial v partial x doesn't make sense. It's dv dx. And here I'm differentiating this with respect to x. So I simplify that down just slightly. And we do the separation of variables now. So we have all of this stuff on, I put all the x's together, and I put all the y's together, and then I have some constants in here. So what I did was I placed everything as a function of y on the left-hand side, and I placed everything as a function of x on the right-hand side, and I arbitrarily stuck the constants on the right-hand side. These are the constants here. You could do it another way if you want. It doesn't matter. You're going to get eventually the same answer. So remember what we're doing. We're separating variables and placing all of the things with x on one side, all of the things with y on the other side, and then a constant on one of the sides. So if that went too fast, just hit the pause button and hit it again. So now, once again, variables x and y are independent of each other. So we've seen this logic before. This can only be true if each side of the equation is equal to the same constant. And some of you are making mistakes on your exams by messing up this very important step. I think it's a super good idea to say the left-hand side is equal to a constant. the right-hand side is equal to the same constant. Don't say that the two of them equal to 0, because you're going to end up with a sign error. And that's what I did here. I have the first equation, and you could see where this is headed because this is a regular derivative.